All right, starting to look at 603, which we're looking at differentiation from first principles. Or basically, we're looking at how we derive or how we get the gradient function. So to find the gradient of the tangent at point P. So what we're doing here is we're looking at point P, which is a fixed point on our curve or on our function. We make h smaller as shown. So basically, we could only find the gradient of a straight line or a tangent at a point. So basically, we are making this point, which is h, or the height that we are varying. So at this point, we go x across and we go h high, and et cetera, and et cetera. So basically, as we come across and we make the height smaller and smaller each time, our tangents that we're creating, the lines between point P and Q, are becoming closer and closer to what the gradient is at that point. So as you can see, as h, or the height we are away from our point, approaches 0, so as we get closer and closer to our point, the gradient of the tangent becomes this formula here, which is, as h approaches 0, we find our function of x plus h minus our original function, or minus our function of the curve divided by our height. And we call this, as we'll see now a few times, these are the three different ways that we can write the derivative function. So f dash of x, derivative of y in respect to derivative of x, or y dash, or basically derivative of y. So that's where we get our differentiation from first principles formula, which is this one. And we're going to be using that to calculate our gradient functions when we're given our standard function. So let's have a look. So calculus notation. On page, we learned about mathematicians Isaac Newton. So Newton used the notation, this is where we get the derivative notations from. He used the notation f dash of x for the derivative function, while another mathematician used the notation dy over dx, where d stood for difference, or if we remember back to a straight line, our straight line, if we're looking at the gradient of a straight line, is our difference in y values in respect to our difference in x values. So as you can see here, this is where we derive it from. So difference in y values, difference in y value, and difference in x values, difference in x values. Again, that's just a bit of background information, not too relevant. So we're posed this question here, and we're asked to differentiate from first principles to find the gradient of the tangent to the curve, y equals x squared plus 3 at the point where x equals 1. So doing it from first principles, we're going to use that first principles formula. So the first step is I'm going to write that formula. So I've got my f dash of x equals the limit as h approaches 0 of f function, where I set variable to x plus h minus my original function, or f of x, over h. So I've got two things here that I need to find. I need to find fx plus h, and I need to find f of x. So coming over the side here, I'm given my original function. Now my original function is my function that I'm given, which is y equals, or I can put f of x equals x squared plus 3. And I can then from that find f of x plus h. So f of x plus h, I simply plug x plus h into my function wherever x is. So I'm going to sub it in here, x plus h squared plus 3. I'm then going to expand my x plus h squared out, which should give me x squared plus 2xh plus h squared plus 3. Okay, so I've got my two two things I need to find. So I've got my f of x, which I'm going to sub into here. And I've also got my f of x plus h, which I'm going to sub into here. Okay, so now what I'm going to factor in is the fact that I'm given x equals 1. So I'm given the fact that x at the point where x equals 1. So I can substitute my x value of 1 into both of these equations here to work out what they equal. So let's substitute x equals 1 into my first equation, or f of x. So I'm finding the function when x is 1. Gives me, wherever x is, I sub 1 in. So 1 squared plus 3, which gives me 1 plus 3 is 4. And then I can also sub x equals 1 into my second equation. So I'm going to be finding the f of 1 plus h. So that gives me, looking down here, subbing this in, wherever x is, I'm going to replace with 1. So I got x squared, which is 1 squared, plus 2 times 1 times h, plus h squared, plus 3. So that should give me, hopefully, 1 squared is 1, plus 3, collecting like terms, gives me 4, plus 2h, plus h squared. Okay, so now I have, or I can sub both of these back into my original equation, sorry. So I should really get rid of, and let's also get rid of, so what I'm subbing in is I'm subbing in my f of 1 value into my f of x, and I'm subbing in my f of x plus 1 plus h value into f of x plus h. So let's substitute that back into the formula. So f dash of x equals limit as h is approaching 0. So sub in my f of x plus h. So I get 4 plus 2h plus h squared minus f of x. So minus, and my f of x was 4. So minus 4. If it was multiple terms, I'd have to apply my negative to those terms, but we've only got one term, over and h, because h is my unknown, which we will later set to 0 in a second. So expanding out or simplifying the top, so I get f of x equals limit as h approaches 0. So I've got 4, take 4, the 4's cancel. So I've got 2h plus h squared over h. Substituting this, factorizing the top, I can see that I've got h as a common in the top. So let's take that. So that equals limit h approaches 0. As you notice, I'm keeping the limit in. So let's bring the h out the front, and then I'll have 2 plus h. h2 plus h over h, which means my h's are common now. I can then cancel them out, and I simply get equals limit of h as it approaches 0 of 2 plus h. Okay, at this point, I now need to factor, now need to factor in the fact that my h is approaching 0. So essentially, h is now becoming 0, or h becomes 0. So if I sub my h value of 0 into my derivative equation, which I'll continue here, so I get, therefore my derivative of my function must be 2 plus 0. So I'm replacing h with 0, which therefore means my derivative of this function equals 2, or basically the gradient equals 2. So the gradient would consistently equal 2 no matter what. My gradient would equal 2 at the point where x equals 1. Okay, let's look at part B of this question, which I've got a bit of room down here. So we're going to differentiate this function using first principles. So exactly the same as what we were doing before, except this time we're not given the fact, or we're not given a point. So we don't want to find the gradient at a point. We just want to find the gradient function. So we could sub in any value of x to therefore find the gradient at that point. So let's write down f of x equals 2x squared. I'll copy that down here. So we're finding the gradient function of f of x equals 2x squared. Let's make that a bit neater. 2x squared plus 7x take 3. Okay, so again, I'm using my formula. So my formula from first principles is my derivative function equals limit as h approaches 0 of fx plus h minus my original function f of x over h. So again, I've got to find two things. I've got to find f of x plus h and f of x. So I'm given f of x already, so I'm not going to repeat that. But let's find f of x plus h, which is going to be quite long for me. So I'll have to probably do it down here. So f of x plus h. So I'm subbing x plus h into everywhere x is in my function. So equals 2 bracket x plus h squared plus 7 x plus h take 3. Okay, so expanding my x plus h squared here, I get 2 bracket. Now we had x squared plus 2xh plus h squared. I can expand this out plus 7x plus 7h minus 3. Cool. So expanding the last bracket now, I get equals 2x squared plus 4xh plus 2h squared. And I'm just going to add on my last bits plus 7x plus 7h minus 3. Next step would be to bring together any like terms which there are not. So at this point, I'm going to have to sub this into my original or my equation at the top. So to make it easier, because it is quite a bit of working, I'm just going to calculate this. So f of x plus h, which is this value, take this value first, and then I'll pop it into my fraction after I find that. So let's just find the top of the fraction, which is f of x plus h, take f of x. So bringing in my value from f of x plus h is this. And then I'm going to add on, I'm going to take away my other function. So here we go. So 2x squared plus 4xh plus 2h squared plus 7x plus 7h take 3 minus f of x. So my f of x was 2x squared plus 7x take 3. So here I can see 2x squared take 2x squared will cancel. Remember that we have to apply the negative to each term in here. I've got 7x here, and I've got a negative 7x here. So they will cancel. When I apply the negative to this negative 3, that becomes positive 3. So my negative 3 and positive 3 will cancel. And that leaves me with 3 terms. So I've got 4xh plus 2h squared plus 7h. And what you'll find when you're doing these is you will cancel out these 3 terms from 3 of the original terms over here. So yeah, you'll find that that's a bit of a pattern that they cancel out. So what I'm going to do is I'm going to plug this back into my formula now. So let me just write, let me fix this up. So save a step of working. F dash of x equals limit as h is approaching 0 of my fx plus h minus f of x, which I found here, over h. Now to cancel my h from the bottom, I can see that h is common in the top, so I'm going to bring the h out the front of the top. So equals limit as h is approaching 0. So h out times that by 4x to get the first term plus 2h plus 7 over h. Now I can see that my h's will cancel. So I get limit as h approaches 0 of 4x plus 2h plus 7. And at this point is when I set my h to be 0. So I'm finding the limit as h approaches 0. So essentially when h is 0 or when there is no height, basically I'm at my point, what is the gradient? So let's have a look. So subbing in, so I now sub h is 0 in here, so I've got my gradient function, therefore equals 4x plus 2, replace h with 0, plus 7, which just equals 4x plus 7. And that is my gradient function. So what I've found here is my gradient function, so I can find the gradient at any x value. So let's say I was asked to find the gradient when x was 2. I'd use my gradient function where x is 2, sub 2 into my gradient function here. So 4 times 2 plus 7, that'll give me 8 plus 7 gives 15. So I can easily now find the gradient at any point of my original function by using differentiation from first principles, which we've done here. So in the next exercise, you'll find an easier method to differentiate, which is much easier, as you'll see. But this exercise does require you to use that first principle formula. So work your way through it and good luck.